Hello everyone, welcome to SES AI Molecular Universe live demo. I'm Chichao Hu, founder and CEO. I'm here with Kang Shui, our CTO, Dan Hanna, Director of Computational Chemistry, Yumin Zhang, Project Manager, and Adam Atanas, Senior Scientist. Before we begin, I want to talk about why we built Molecular Universe, our motivation. So we live in a world where you have renewable energies and storage that provide power to consumption. Your data centers, EVs, drones, robotics, and then they generate data that train our model that discover new materials for new energy. But this material discovery process is actually really slow. It takes a lot of times for EV batteries more than 10 years, from R&D to A samples to B samples and then C sample and then commercial. Now, we're very fortunate that we made it to B samples in lithium metal with 2 OEMs. But then a lot of customers ask us, can you provide your powerful material discovery tool to other chemistries, to other applications? So that's why we built Molecular Universe. It's a software and service platform that works for all chemistries. So obviously lithium metal, we do that better than anybody, but also silicon, LFP, sodium. We want to apply Molecular Universe, this platform, to all chemistry and across all applications. Now, in traditional material discovery, a human scientist uses experience, years of experience and knowledge. That's great, but there's always a limit to how many molecules a human scientist can explore. And this is why a lot of times a material discovery is based on luck. So what we want to do is build an AI agent that is trained on the entirety of battery relevant knowledge. All the molecules, all the properties, all the papers, all the books, literature, all the internal data, and then we take all that to train this AI agent. And of course, we're not just recommending molecules on paper, we also synthesize these molecules, and then we test the molecules, and then we formulate electrolytes, and we build batteries, A samples and B samples, and then we validate all the cell level performance, and then we feed all this data back to training this model. So really our goal is to build artificial superintelligence for energy transition, replace and accelerate R&D. So, and without further ado, Kang, you want to tell people about the map of the Molecular Universe?
Sure, I'd be happy to. So as Chichao mentioned, in the past, human scientists has been searching new materials and new molecules on the basis of serendipity. And that way is by no means exhaustive and not rational, so we want to change that. That's the whole purpose of this molecular universe, by which we calculated over 100 million molecules. That's a tiny fraction of the whole molecular universe, but already orders of magnitude larger. And how can we do this? Helped by the hardware developed by NVIDIA, GPUs, helped by these new software techniques, accelerations, AI, machine learning by our partner again, NVIDIA and others. So what you are seeing here is a map, we call it the U-map, map of the universe. Long story short, this is the dimension reduction of the representation of 14 million molecules. Like I said, we calculated more than that. This only represents 10% of the calculated molecules, but it's really huge. And click please. We applied the electrolyte constraint we developed here, which consists of different structure requirements as well as DFT, homonormal ESP, min-max. So all these molecules which pass the constraints of electrolytes are represented as yellow dots here. As you can see, even in this small sub-universe, 14 million only, very tiny part of the molecules which occupies the entire universe. And based on that, we also extracted all the chemicals, solvents, additives, co-solvents ever used by the battery scientists in the past 10 years. We plotted those in green. As you can see, that very tiny fraction of the universe, even this sub-universe, is occupied by the chemicals explored by human beings. So that shows us that there's still huge space, chemical design space out there, remained untouched area by human beings. And all we can do today, assisted by the software and hardware advances, by machine learning and artificial intelligence techniques, we're able to explore this molecular universe in a much more exhaustive and rational way. On this map, we also overlay the most known chemical compounds, as you can see here, ECPC, DMC, and some fluorines. They are all clustered together by the structure similarity. But this map, what this map provides with us is that not only you can search for molecules with a similar structure, but also molecules which are very different in structure, but with very similar properties. So I would hand this up to the project manager, Yu Ming. He will introduce you to the user interface of the molecular universe, which is based on this UMAP representation.
Thank you, Kang. I hope user can see my screen right now. So on the this is our molecular universe main page. This is actually very easy to find this main page. So this will be linked to our SES AI main website. You can just directly go to Molecular Universe and find our service here. So in our Molecular Universe, we have four main features. The first one is map, second one is ask, third one is search, and fourth one is filter. So we're now at the map feature. As you can see in the center, we have this map. And this map is very interesting. So this is the way we help user to visualize millions of molecules and in an interactive 2D way. And we use technique called UMAP. So Dan, do you want to introduce a little bit more about UMAP?
Yeah, sure. So I can start by talking a little bit about what the motivation for this map was. So if you imagine that you wanted to explore the United States, but you only had a budget of 10 cities to visit, you would, if you didn't have a map, there'd be a chance that maybe you just picked 10 cities all on the East Coast, for example, and then you didn't really get a sense of what kinds of things were around the entire country. So the reason we initially built this map at SES was actually to ensure that we were kind of adequately exploring this molecular universe. And what we really needed to construct that map was a way of measuring distances. So just like when you're building a normal map, you might need to know how far apart two cities are. We needed a way of quantitatively measuring how far apart two molecules were. And so the thing that sort of provides that for us is a tool called a molecular fingerprint. And a molecular fingerprint is actually 512 numbers that characterize a molecule. So what that means is that on the back end, each of these data points that you're seeing is actually 512 numbers that describe each individual molecule. And that 512 sort of dimension is a lot, but that's actually what's required to capture sort of the richness and complexity of structural chemistry. The issue is that humans can't really visualize or reason in 512 dimensions. And so like Yuman mentioned, we applied an algorithm called the Uniform Manifold Approximation and Projection, or UMAP for short, to take those 512 dimensions and reduce them down to 2, something that we can visualize. And indeed, that's exactly what you're seeing here on the Molecular Universe website. But the magic of UMAP is that it does that dimensionality reduction in a way that preserves both global and local distances in the higher dimensional space. So what that means roughly is that when two data points on this map are close together, they are structurally and chemically similar. And likewise, when they're very far apart, we expect them to be very structurally and chemically distinct.
So this is really like a Google map, but it is for chemicals, right?
Exactly, that's right.
Yeah, so there's some features to our UMAP here. So our users can actually hover around the UMAP. You can see when I rest my mouse in a molecule, you can see the molecular card information pop out. You can read there are homolumo levels, molecular weight, and other informations. And you can also zoom into area, like you can do for a Google map, and try to discover the treasures here. So and then I think there's another interesting thing on this map is we use a different color to represent clusters. So clusters means that molecules have a structural similarity. Can you tell us a little bit about how we clustered them?
Yeah, absolutely. So as you can see, the scatter plot actually naturally stratifies into these different clusters or islands or continents. And what we find on manually inspecting these is that they are grouped in ways that fundamentally make sense to a human chemist. And so you might see that, for example, carbonates are in a particular cluster, and you might find ethers in a different cluster. And so ultimately, we wanted a way of sort of automating this and using those sort of cluster labels for further sorts of exploration and data set building. And so what we did is we applied something called a clustering algorithm. And the results of that clustering algorithm, which basically endeavors to automatically discover the natural divisions in the data, are actually what's driving the different colors for each of these islands on the map. And so one thing that we did after we sort of applied this clustering algorithm was we sat down with human chemists and experts in the field, and we reviewed what types of molecules we can expect in each cluster. And so that's what this cluster descriptions guide is providing on the bottom right here.
Yeah, so I find actually cluster 9 is a very interesting one. If you remember the slide that Kang just showed, cluster 9 has a high population of molecules that could be battery relevant. So for users, you can just go to the cluster 9 here. You can see this is largely populated by non-aromatic monoacylic sulfones. So that is an interesting feature for our map as well. So this is about map, and the next feature we have is ask. So ask is a very natural way for users to interact with our giant database. And so this is the map. We have the map, and now this is our navigation system. So Adam, could you tell us a little bit more about ask?
Yeah, be happy to. So yeah, so under the analogy of sort of map being sort of Google Maps, where you can just sort of like zoom in and out on like a different country. If you're in a country, you might want to know things like, what are good places to eat around here, or things of that specific nature. You might want specific details on what parts of the map should I be looking at. And what we did with Ask is we really built this tool to try to be really useful to battery scientists trying to like find their way around the map, guided by the sort of large amount of human scientist research and literature that we already have produced as a field about basically which types of molecular properties are useful for synthesizing batteries. So basically Ask is sort of comprised of sort of three key components: literature search, large reasoning model, and integration with the molecular universe map. So behind the scenes, when you enter a query into Ask, Yuman, do you want to go ahead and
oh yeah,
something in?
Of course. Yeah, I will type a question.
Yeah, so while Yuman's typing that, I can keep explaining. So behind the scenes, when Yuman types this query into the Ask, what happens is it gets entered into our literature search feature. So basically what this does is it searches for this query against our database of over 10,000 battery relevant papers and textbooks that we've carefully curated from the field. And importantly, we keep this database up to date every month with the latest research, so you can be sure that your query will have access to the most cutting edge information. And then what happens is this query plus literature context is then fed into a cutting-edge large reasoning model. So we picked a large reasoning model instead of sort of a more traditional large language model because we really want the model to be able to think for a while about about your question, about all the literature, thinking about how to apply the literature to best answer your question using its own internal knowledge, and so on. We really want it to produce a very high-quality response. So. And what the goal is basically between the literature search and the large reasoning model, we can really get around a lot of the traditional limitations of large language models. For instance, our models are much less likely to hallucinate because they have access to cutting edge research. They also, because they have access to the most recent literature, we can also bypass the problem of large language models having a training cutoff. And so in this way, you can really get these like really high quality answers from the large reasoning model in the Ask feature. And then the third thing we wanted to do, we didn't just really want this to be sort of like a separate chatbot window. We wanted this to really integrate nicely with the map and with the rest of our database. We have this database of 100 million molecules. We want to be able to, if once a model answers with a set of molecules, you really want to be able to go interact with them, play with them, and see sort of how they look in our database, which molecules are similar to them, and things like that. So in a few seconds here, hopefully the model will be finished thinking, and we can see that feature there.
And by the way, this question is really natural. Like most customers, a battery company or a car company will basically start with questions like that. Like, I'm currently using this cathode, this anode, this formulation. Help me improve the formulation so I can improve, in this case, fast charge or safety or what have you. So it's a very natural way for customers to ask questions. But yeah.
Yeah, Kang, what do you think
Sure.
about the answer?
I'm looking at that. So this question is about the high anode NMC 811 lithium-ion battery, and we are asking to recommend the formulations that can replace the current FEC-based electrolyte. So it gives a list of the very nice salt, solvent, or well-organized and additives. And seems to me those answers are from professional battery scientists would be seeking to. For me, if I want to look for those answers in the literature, it take me like an hour, fastest half hour, and this takes a few seconds. And you can scroll down to the recommended chemicals. Usually it's at the bottom. It summarizes all the salts, solvents, co-solvents, additives. It mentions there. You can click on the find molecule. It will bring out the molecular cards which have the calculated DFT data, and machine learning model predicted property data behind that. For example, yes, scroll down, and then let's see. So this one still has FEC. Let's further refine the question by asking that since FEC generated some gas during cycling, can we find a replacement or a better formulation to replace FEC and see how the model responds?
Since fluorine acid carbonate generate gas,
FEC normally generates gas during non-cycling or high temperature storage.
Can
so
we find a molecule?
recommend a molecule which replace FEC in the above formulation.
Uncheck the box down there also.
Right.
I did. Can you find a solution?
You
Yes.
find a molecule to replace it.
Replace FEC.
Yeah, to replace FEC.
Yeah.
So I want to mention that this MU-0, that's our current version of the molecular universe, only contains neutral species, which are either solvents, co-solvents, or additives. But in the future, we are going to integrate a map for the anion, which will encompass all the lithium salts or sodium salts, potassium salts that it could be come across.
Yeah.
Now the model is thinking.
This is more than just a chatbot. Like it actually answers questions for you and then solves very practical and then natural questions.
That's right. Yes. So for most of the battery scientists or engineers working in the either battery companies or car companies, they don't use smile string or very chemically related information. They prefer to use natural language, and this is a powerful portal. Now the answer comes out, and let's take a look at the. Okay, now it recommends a few more chemicals, additives that can replace FEC to suppress gas generation. Those are the chemicals which look very exotic, but I'm sure that there's literature basis for that. Exotic means that for normal, thinking when you design electrolyte, you would not naturally think of those because most of the people are only thinking about EC, DMC, or carbonates. Let's just scroll down to the bottom and take a look at the chemical summary there. And meanwhile, click the find molecule, please. To bring up the new molecules mentioned in this answer. So you can either go above to look at the formulation recommendation. You can also go at the bottom, which recommends the different chemicals, which might be very different in structure from FEC, but with similar properties, so that you can use them as a drop-in replacement. So there's one molecule it recommended, that's anhydride is the first one. Let's just choose this one and click find its own friends. You can find the that yellow. Okay, yeah, good.
Yeah.
So those chemicals could be very different in structure. You can scroll down and use the entire. So by default, we recommend 20, or right?
Yeah.
Yes,
20.
Yeah.
But that number can be changed, yeah, according to the
That's flexible.
level you. Yes.
That's right. Yeah, and I can comment a little bit on this too. When we are returning these results for the find similar molecules feature, we deliberately endeavor to show some molecules which are structurally similar and also have similar physicochemical properties to the molecule in question. But we also try to pepper in some results that are structurally distinct while still preserving similar physicochemical properties.
So this really help our researchers to explore and brainstorm.
That's exactly right. And that was one of our original motivations for building this tool internally, which we obviously decided to make available to the public after seeing how useful it was to us. The thing that this really adds value for is discovering molecules that are nevertheless well suited for a particular purpose that a human chemist may not have even thought of.
Yeah.
And that's why we try to pepper in some of those results which have sort of a different structure but similar physicochemical properties.
Right.
So that actually answers one of the questions I'm seeing right now from the audience, which the audience who asks that does that only provide the structures from literature, or does that give us new recommendations? Actually, the first panel you saw there on the right, those chemical structures are from the literature. However, once you click those yellow buttons, find friends or find the similar molecules, then the molecule structures come up, are nowhere, I mean, most of those are nowhere to be found in the literature. Those are the purely AI recommended.
And those are from our database.
Yes.
Yeah.
Yes. Those are the calculated molecules.
So basically, from a customer's perspective, the customer may not be familiar with molecules. It might be a car company, might be a battery company, and then they start with this question in natural language: improve the fast charge of this particular chemistry, and then it will answer it by looking through all the literature, providing answers from the literature, but then also recommend new molecules in this broader molecular universe that are similar to the answers.
Yes.
So
by comparing
first,
the properties.
yes. So first it gives a known answer, and then it provides recommendations of new unknown but similar molecules.
Yes. Exactly.
Yeah. So how about we move on, and we'll come back to ask to use our audience question later.
Yeah.
Okay. So the third feature we have is called search. And search is a way for our users to easily access our database. So in search, we actually take 3 kinds of entries. You can enter, if you know the small string of the molecule you're searching for, you can enter the small string directly. If you know the name of the molecule, you can enter the name, or you can use natural language to search the database as well. So Dan, how about let's try something here?
Yeah, so let's carry forward some of the molecules we were focusing on the Ask tab. And why don't we start with fluoroethylene carbonate?
Sure.
Which is probably one that's familiar to a lot of people in the community.
That's FEC.
Yeah.
Yeah.
Yeah, when we were saying FEC earlier, that's fluoroethylene carbonate.
Yes.
And I will check the Find Friends box here.
Sure.
I spelled it correctly, right?
We have a lot of users interested in silicon batteries.
I think so. Yes.
Yeah.
So as you can see, when you enter a molecule for searching, you will see the molecule is actually flagged on the UMap here, and it's flagged using the tab says search the molecule. And since we checked the Find Friends box there, so it will also return 20 friends that are related to FEC, and those friends are also labeled on the UMap. As you can see, they are actually spread out in different clusters on our UMap. So Dan, do you want to explain a little bit about our molecules here?
Yeah, absolutely. So one of the things that I think is worth emphasizing is the different use cases for ask and search. So again, to sort of lean on the road trip metaphor from earlier, when you're using ask, it's more like you have an experienced travel agent helping to guide you through the journey that you want to take. In other words, helping to decide where should I go next in this molecular universe. And sometimes that's what you want. Sometimes you actually want to build on that sort of collective expertise that we were able to incorporate in the language model that powers ask. On the other hand, sometimes you sort of want to set off on your own and explore in a way that for both better and for worse can be totally unbiased by sort of pre-existing human knowledge. And that's really what search is about. Search is sort of a direct portal for you to interact with the data without sort of any assumptions in the middle. And so one of the things that Human has demoed here is this ability to, again, sort of find molecules that are similar to a query molecule. So when we searched for fluoroethylene carbonate, you can see that that molecule, which is at the top of the list, was surfaced first, and we have a list of properties that are related to that molecule, and in particular, how it's likely to perform in an electrochemical context. But then we have all these molecules that, by virtue of the fact that they have similar physicochemical properties to FEC, could potentially be stand-ins for FEC in a given application. And some of these molecules sort of very clearly have a structure that is similar to FEC, but other molecules look totally different. And again, that's actually one of the core use cases that we found internally for this tool, was that we sometimes wanted to explore an entirely different class of structures that we felt would nevertheless perform the same way from an electrochemical perspective. And that's one of the ways that we've been applying this internally.
Yeah, this tool is pretty cool. It's actually you can get the small string and also the molecule from ask, and then you can paste it here, and
That's
you
right.
can do your search, right? So I also want to demo the how user can use a natural language. How about we try that?
Yeah, sure. So like Human mentioned, this search box can also respond to natural language queries. So rather than having to sort of programmatically find a smile string or be very precise with your language, you can actually frame your query in the form of a plain language question, just like Human is typing out here. And under the hood, this will actually be translated into a set of results that captures the question that was asked.
Yeah, so as you can see, I said I wanted to see 5 molecules that have HUMO level lower than -7 eV and the LUMO level above -1 eV. So it does give me 5 molecules. If you want to know more about the 5 molecules, you can actually copy the small string and enter to the search entry, and you click on the find friends. It will also find friends for those molecules as well.
That's right.
So this is a very powerful tool. As you can see, those molecules are also plotted on the UMap. So I really enjoy using the search feature as well. So we also have another very cool feature, which is called filter. So if you already know the molecule that you're looking for, say you're looking for molecules that has a molecular weight, let's say above 188, and then you want the HUMO level that is in the range of -9 to -7, and the LUMO level, let's say, from -0.60 to above 1. So you can actually play around with the filtering bar, and you can stack them as well. And as you can see, once I sliding the filtering bar, the molecules on the map will decrease. So that means we're helping users to filter out molecules they don't want. And then you can also select the functional group that you're interested in. A lot of molecules are esters, a lot of molecules are ethers. You can actually click that, and then we'll filter out the molecules for you. You can hover around the map and see what are those. You can also copy paste those small strings back to search and explore those molecules furthermore. So are the main 4 features of our molecular universe. Do we want to go back to ask and try some questions?
Maybe we go back to search and then just do one more, like find a friend.
Yeah, of course. Do you have any molecules in mind?
EC.
Okay.
It's ethylene carbonate.
Yes, I think this one, and then Dan, if you want to talk about the exploration and the exploitation, the two aspects.
Yeah, in terms of, so that's right. So Qichao mentioned exploration and exploitation. So effectively that's balancing trying to kind of thoroughly explore a given neighborhood of this map versus getting a diverse sampling of all of the regions in the map. And so the thinking is that if I have a query molecule, there's a very good chance that the things that are right around it in the map are going to perform similarly, because to some extent chemistry structure dictates function in many cases. And so there is a lot of value in actually seeing, if I have a molecule in mind, what are the properties of the molecules that are sharing its local neighborhood? And there's a lot of value in thoroughly exploring a neighborhood of this map for a given application. But then at the same time, like we said earlier, there's this idea that there might be useful surprises lurking elsewhere in the space. And so that's why we also strive to bring in some of these molecules from other clusters, from other regions of the map, in order to give the user the ability to carry out that exploration piece and make sure that they're still able to discover anything that sort of chemical intuition would not have led them to naturally. And then the reason that we keep things to sort of a similar set of physicochemical properties is because we feel that's what gives us the best chance of having, even though structurally distinct molecules, still being useful for a given application. So just to give a concrete example there, right? The HOMO and LUMO values, that stands for highest occupied and lowest unoccupied molecular orbital, those are roughly related to the electrochemical stability window of a given molecule. And so even if you're looking for molecules that are structurally distinct, it's very likely that you'd like to have the electrochemical stability window be similar. And so that's why we constrain the properties to be similar, even as we try to balance exploration and exploitation in the categories of structures that we return to the user.
And this is an evolving map.
Absolutely.
Like we have 10 to the 8th molecules, and then it's not just limited to solvents and additives. We are going to add more organic molecules, more inorganic molecules, more charged molecules for salts, and also all the properties we list: molecular weights, HOMO, LUMO, ESP, functional groups. But we can also add melting points, boiling points, solubility, viscosity, conductivity, even SEI. So it's really an evolving map. And then
That's right.
In the first version, MU-0, this is what you have, but then in the coming versions, we are going to add more molecules to this, so users can find more molecules and also more properties. So it's easier and then more accurate to find like real friends.
That's right, and that's a really important point. This isn't a static database. This is something that's constantly evolving. And I just also want to emphasize what Adam mentioned earlier, which is that as we're adding molecules to the database, our literature database is also constantly growing and evolving.
Yeah. Yes.
And that's a really important point, because I think the rate of publications, particularly in battery science, makes it almost impossible to keep up with the state of the art and sort of what's evolving in the literature manually. And so to have this tool, which is effectively a living window into the state of the art from the literature, is actually very useful to save time for scientists who would otherwise have to crawl the literature themselves and make those summaries themselves.
And also for some users, say they are interested in a particular property, say solubility, we can actually compute that for them. And also the way we rank our friends, it's basically equal weights on all these properties, right? But if a user comes to us and say they want a different ranking preference, we can also adjust that.
I just want to add something. I have been looking at these questions online, trying to answer a few. So one question I want to bring out is that some people users are trying to look for a few salts there. Like I mentioned, the current MU-0 only contains neutral species, solvents, co-solvents additives. But in the future, MU-1, we are going to add the anion map, which will provide you with the salts.
Yep.
And the anion map, anion database is under construction right now, soon to be released.
Yeah.
That's right.
This is a map of neutral molecular universe.
Yeah.
We're going to introduce a map of charged molecular universe later this year.
That's right.
Yes.
Salts
Yes.
are coming.
Yes.
Yeah.
Yes.
Both cation and anion. Another question is about the if this only applies to lithium-ion battery. The answer is that it's agnostic of the battery type.
We can
actually.
try a sodium now.
Yes.
Maybe
So
we try.
I want to invite audience to give us a question we can type into the chat.
So we try one more question on sodium.
Sure.
And then we get to the audience question.
Sure. Oh, you were logged out?
I was locked out.
Too much
yes.
idle time.
Okay, yeah.
Okay. All right.
Sodium. Yeah.
We try a sodium question.
Yeah.
Okay.
Recommend the electrolyte for sodium-ion battery consisting of hard carbon anode and let's say sodium iron phosphate cathode that can support fast charge and low temperature operation, which we can just adjust the requirement in the question.
Is this the question?
Yes, good.
Yeah.
Yeah.
Okay.
Yeah. Let me see.
I actually wish I could have this tool while I was doing PhD.
I wish I had that, which was 30 years ago.
Yeah.
But we tried this for silicon, for LFP, and now it's sodium. Yeah, we did try this for different chemistries. Yeah. Oh.
So we got an answer.
Yep. Let's take a look.
So it's giving you one formulation, and also safety.
Mm-hmm. Yeah.
Because we specifically
Yeah,
asked
yeah.
for one
Yes.
formulation.
Yes. Yeah. Yeah.
Okay.
And sometimes in the prompt, the more detailed the question we ask, like the more information about the cathode, the anode, the charge rate, discharge rate, voltage, the more specific it's going to answer the question.
Yes.
Scroll down to the bottom and take a look at the chemicals. Okay.
ECP.
You can try find those molecules and show those in the molecular cards. Right. EC is still our favorite, but sodium-ion battery doesn't confine to EC. You can use also PC because there's no graphite there, and a bunch of different additives and salts. But again, salts cannot be shown here. It will be in the future MU-1.
That's right.
Yes. We're constructing the anion map, and possibly for the cation map in the future for ionic liquid discovery.
Yeah.
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 Good.
Now, shall we go to the audience question?
Sure.
Okay.
Do we have any question from audience? Then we
Yes.
can type into the
You can just
chat bot.
pull it up, see what you see. Yeah. That's good. That's good. So just show that on the TV. Okay.
Do you have a question now?
Which one
You got a question?
Also,
Some of the
lot
questions are too
yeah.
general. Yeah.
a lot of questions. Let's focus on questions for this molecular universe tool first.
I can scroll down to the bottom
Yeah.
and wait for the new one.
Yeah. Okay. Oh yeah. I think
There's one
that
on the
one.
there's
Yeah.
one on the bottom
Yeah.
there.
Okay.
Lithium metal is
Yep.
perfect.
This one?
Yeah.
Yeah.
Think of electron
Can you ask the
formulation,
question? Think of the electrolyte formulation. Yeah. Let's try that one.
Critical cost.
That's a chemistry and
Yeah.
material related question, not too general.
Yeah. That's a lithium metal battery. What's the cathode? NCM cathode. And then
Let me see.
yeah,
I'll
current
just,
formation. is
Loading
that.
area loading.
Yeah.
Lithium.
Okay. I will send
Yeah.
this question now.
Yes.
Too many windows opening up.
Maybe it's gonna show our own secret formulation. But
Hope
We'll
not.
see.
So while this thinks, I can speak to one of these questions. So there was a question about whether the molecules in the database are real and stable. The short answer is yes. So in the current version of the database, all of these molecules are real. And so we also have verified their stability on the back end through physical simulations and calculations. Eventually, we do endeavor to expand this database to include molecules that may not have yet been synthesized, so we can sort of expand the discovery potential of the database. And when that happens, we'll apply that same level of computational scrutiny to those molecules to verify that they are at least stable, even if they haven't been synthesized yet.
The answer is here. Seems it recommended the local high concentration electrolytes with TFEO, FDMP, and see if we can find those molecules. We can directly go to the bottom. Yeah.
And
This
also,
is
if you want,
it's a short name.
if you want more information, also you can, of course, the references that from our literature database that were used to generate the response are always highlighted here, so you can go look at them yourself if you
You can
want.
follow up the
more
question by
in-depth,
asking what the TFEO is, then
Yeah.
it can find it. I know TFEO using the database. Because
TFEO.
the
Yeah, what
literature
is
only
TFEO?
gives you a acronym, so acronym cannot be found on the map.
It's a
It has to be a
solvent.
real chemical name. But in literature, it gives you reference, so through the reference, you can easily find what TFEO is.
Right.
Those literature links are very useful for students who want to study more about
Right.
the
Yes.
Yeah.
But for me, if I'm a PhD student working for my on my thesis, I prefer the find friends, sort of function, which give me, connection to the structures that can never,
TFEO
using
solvent,
human
yeah.
brain can never think of.
Yeah.
Those are the real ideas, original ideas.
So come.
I
Just,
cannot see; it's too small here. Oh, it's larger there.
Yeah. It's
Okay.
big on top.
You can click the find friends. Find molecule to see if.
Oh, yeah, yeah,
Okay,
it's
now
there,
it's
yeah.
larger.
DME.
That's DME. Yeah, it's the one of the solvents recommended there.
But you
It
have the
might be.
name of TFEO at the top, right?
Yes.
At the top, just copy
You
and
can
paste.
directly search that. Then, yeah. Tries
Copy and paste.
222 something. Yes, it gives the name. Yeah.
This one.
Yeah.
And the find again.
I think go to search. for
Search.
that.
Yeah.
Okay.
Oh, this is 1 million data set, right?
This
Yeah.
is the
Okay.
1 million
Okay.
data set.
Yeah.
Yeah.
It's in the larger set. I know it's in
Oh.
the
Yeah.
35
might not
million.
be
It may not be
That's-
here.
Yeah, it's
It
possible.
might not.
apologize, yeah.
It might not be in
Correct.
this one
It's not
because
in
we
the
have
set, yeah.
We'll talk about
Yeah, this
pricing later.
Yeah.
And-
Yeah.
The
We are-
account that
we
I'm
are-
showing you now is the one that
Yeah.
is going to be free to use for
Yeah.
all academic researchers.
This is the free version.
Yeah.
This is
Yes,
free
this
version.
is the
you'll
free
see.
version.
Okay.
Yes.
Uh-huh.
Yeah.
Yes.
We're showing you the exact same thing
Yeah.
that you'll get access to.
Yeah. Yeah. Maybe a few more questions from the
Let's
audience.
try another question. Yeah.
Okay. Do we spot any questions here?
I haven't. Most of the questions are curiosity about the MU-0 itself.
If you scroll up a bit,
Okay.
there's for novel battery relevant molecules, not
Yeah.
how critical is the cost? So that's a sort of a different question, but
That
could be interesting to try, given OEM preference for commercially viable.
Or I can ask a question of my own.
Sure.
Try it.
Okay. So we asked about lithium-ion battery. We asked about sodium battery. Now I want to ask a question about silicon anode. Yeah.
Great.
You want to address that one? You guys talk about this reasoning model.
Oh yeah, so sure, I can talk about
What's your
it.
type? Yeah.
Susie's question there. So yeah, so generally, I would expect these reasoning models to have some ability to reason about entirely novel molecular structures. Obviously, if you're asking about a molecule that nobody's ever experimented on before, there's going to be less data to go off of than a model that's been extensively studied in the literature. But the models do have these reasoning models do have some innate chemistry reasoning capabilities, so they will be able to produce a response to those types of queries as well. That should be reasonably accurate as well. But obviously, for an entirely unstudied molecule, no human or AI is going to be able to perfectly predict what the molecule is going to do. At some point, you're going to need to go into the lab and actually experiment on it. But yeah, I think in terms of just getting a baseline summary of things that the molecule is likely to do, I think our model should be able to handle that.
I want to bring out a question asked by the audience here, asking about how we predict. Are those just DFT calculated properties, or are there predicted higher level properties related to the electrolyte solution and ACI formation? That's a good question.
Yeah.
So short answer is yes. Currently, the MU-0 contains most of the DFT calculation on the single molecule. However, we do have a few properties, physical properties for the condensed phase, which are given by the prediction models of machine learning models we built, which were trained by large sets of data. And we're also in the current efforts to add more MD simulations on the electrolyte solution level, as well as the new ACI prediction tool. Those will be available perhaps starting from MU-1 to MU-2, MU-3. We're constantly updating the tool. Yeah.
That's right.
So we have the answer to your silicon question.
Okay.
Yeah.
Yes.
Yeah. So I just asked a question about give me a list of solvent additives that can slow down or prevent silicon anode expansion, which is a very it's a question that actually a lot of people care about.
Okay.
Yeah.
And let's try to find molecules again. I want to show some structures and some molecular cards.
The FEC, VC, PS, DMC.
So Saltone and
Yep.
Okay. So yeah, some of the structures may not be available in this free version, but they will be in the larger paid version.
Yeah. Yeah. There was one question about, does this work only for non-aqueous? Does it work for aqueous?
Well, for aqueous battery, the solvent is already fixed. That's water, right? You don't need to search that. The only thing you need to search is the salt anion, which will be in the anion map we are building.
Okay, good.
Yes.
Good. I think maybe we have time for just one other question, and then we cover the pricing. Yeah.
Okay. Let's find one question from audience. I still want to field this question from audience. Can we pick one?
Variable DFT functionals, what accuracy? If we don't see a question, we can also talk about, how do we know if these DFT MD calculations are accurate? Like, what metric do we use for that?
Well, DFT is a pretty mature tool, so I can let Yuming and Dan explain later, but I want to emphasize on the MD part. MD simulation accuracy really depends on the force field you are using. So we have this unique polarizable force field which gives us very accurate prediction of the solution level properties such as ion transport, viscosity, solubility. Those are really hard to do, and that's something you cannot find in the literature. So MD data is not available in the MU-0 yet. However, they will be available in the later versions. For the DFT, yes.
Yeah, so I can speak to the DFT a little bit. So basically, as practitioners probably know, that the sort of quantitative value of, say, the HOMO and LUMO is something that very much depends on the settings that were used to run the DFT calculation. So what's really important in our case is that we essentially correctly order the relative stability of, say, various solvent molecules or various salt molecules once that database becomes available. And so that's something that we have vetted in-house. So basically, we've parameterized these calculations to be mutually compatible across the entire data set and have vetted them for their accuracy in correctly ordering the experimentally measured stability of these solvent molecules in various kinds of testing regimes and data sets. And so we sort of stand by the ability of the parameter sets we've used to render predictions that should correlate with what someone would go and measure in the lab. But of course, it is absolutely true that if someone were to run these calculations using different settings, the absolute values of those HOMO and LUMO numbers may and indeed will be different because they're a property of the exact basis set and functional that was used.
We just got answer to the question about slurry mixing for cathode and anode.
Yeah, so one of the audience asked our model to make some suggestions for slurry mixing for cathode and anode materials. So here is our answer. Kang, what do you think of that answer?
That's too small for me to. Right now, it has a split screen. Okay.
On the big one, maybe?
Yeah.
Huh?
The poll is very awkwardly placed.
So it does give.
Can you read out the answer?
Yes, I can read.
cannot see
I can
from
read the answer. So
here.
it does give some rule of thumb
Okay.
for preparing both cathode and anode slurries. First, it shows you. It tells you how to choose your recipe, and it tells you about what active material loading is. So you have cathode. There's a couple of choices. There's anode. Anode is graphite. And it also gives the weight percentage of the solids, and it also shows you the conductive additive.
Okay.
So you have percentage of those.
That's a very decent answer. Yeah.
And then it also tells you need a binder. So it also tells you what kind of material for that. It says
I think it's pretty
decent.
It is
Yeah.
pretty
Specific, yeah.
decent, yeah.
Yeah.
And it also gives you the order of
Even the
addition.
calendaring conditions even. So those are very detailed.
Yeah.
Yes. So I think for a researcher, you can just look at this
Gansing panel.
this
Yeah.
recipe and
Yeah.
start doing your experiments.
Yeah.
Yep. This actually is more related to the engineering and design, manufacturing design.
Yeah.
Yes.
Our goal is to eventually add, in addition to molecules, but also electrode formulations, cell designs, process, including cathode coating, anode coating, and basically provide this entire tool for R&D. So let's go to pricing tab, and
Sure.
yeah. So we offer 5 tiers of access to everyone. The first one is anyone with an EDU email can use this for free. And we do have a limit of 100 queries per month. And then if you pay $150 per month per user, then there's no limit. And also $1,000 per month for 10 users, and there's no limit. All these are pure software based, and users can access the 1 million partial molecular universe. If you go down. And we also offer 2 servers types. One is enterprise, and then one's joint development. Enterprise, it's basically access to the entire molecular universe, 100 million, 100x bigger database. And this one, we can do on-premise deployment. We can custom compute properties that users are interested, and then we can also add more properties. And we can also, so as part of on-premise deployment, we can also put our navigation model and have the customer input their own data, and then train this model with their own data. So we can license our map, we can license our navigation system, and have the customer custom train this so that the answers are even more specific and it's also secure. joint development is basically everything in enterprise, but then we also synthesize molecules, we test batteries, we do the whole thing, A sample, B sample, the entire project. So basically Molecular Universe first version, MU-0, is now live on our website. You can go to ses.ai and then go to products. It's listed there, and we would love to hear from you, your comments, questions, and then hopefully we can make Molecular Universe better together. And as the team mentioned earlier, later this year we will be releasing new features, new molecules, new properties, more powerful, more advanced navigation tools. So hopefully we can make this even better for everyone. So
Yeah.
thank you, everyone.
Thank you.
Thank you.